example from a previous exercise, we will build several compensators and try different set point functions at the set point input: exponential, linear, smooth step, and smoother step. For these examples, we are adding the restriction that the plant input can't be negative and it can't exceed 1 over the plant gain. This gives us a plant output in the range of 0 to 1. Let's build a compensator now, specifying exponential output and 90% in 18 steps. Copy-paste the coefficients from the data window into the spreadsheet. The compensator coefficients appear here with an integrator and the plant model. As we can see, we do indeed achieve 90% in 18 steps. There's 90%, 18 steps. Notice how the compensator gives an initial big push in the positive direction and then recoils in the negative direction and then settles at 1 over the plant gain as expected. Here's the initial big push, here's the recoil, and eventually settles at 1 over the plant gain. Now we will build a compensator that achieves 100% in one step. This may appear to be ridiculous, but it is possible under restricted conditions. We specify linear output, 100%, and one step. We copy-paste the coefficients into the spreadsheet. The first strategy is using a linear ramp at the set point input. Initially, we are ramping the set point 10% on each step. And here you can see it ramping up to final terminal value. We can see that the disturbance at the plant input is mostly contained, but the problem is the plant input overshoot at the end of the ramp. It overshoots almost 8% right here. One idea might be to allow a small buffer at the set point extremes. Let's try limiting the set point to 0.95 instead of 1.00. Now the plant input remains in range. Let's adjust the slope and set point limit to find the maximum performance. To summarize this strategy, we are using a very aggressive compensator that achieves 100% in one step on its own, and then controlling the system behavior by ramping the set point up to a maximum value slightly less than 1. This strategy achieves 100% of the maximum set point in 8 steps, but the set point is restricted to a little less than 1. Let's try using a slightly less aggressive compensator, say exponential, 90% in 3 steps. Copy-paste the coefficients into the spreadsheet. Now we see a linear ramp followed by an exponential, with no set point restrictions, achieving 94% in 6 steps. Here's the linear ramp, a little exponential at the end. Six steps, 94%. Compared to the baseline compensator of 90% in 18 steps, that's a significant improvement. Now let's try smooth step at the set point. You can see the smooth step output here. Let's find the best performance with smooth step. 6 is too fast. There's overshoot on the input right here, almost 13%. But 7 works perfectly. Everybody's in range. The output's in range, the input's in range. There is no set point input limitation, and we are achieving 100% in 7 steps. %, 7 steps. Now let's try smoother step at the set point. You can see the smoother step output here. Let's find the best performance with smoother step. Eight steps is too fast. You can see a little input overshoot here of a little over 4%. But 9 works perfectly. There is no set point input limitation, and we are achieving 100% in 9 steps. Nine steps, 100%. These are very good results compared to the original exponential output achieving 90% in 18 steps. All of these strategies involve plant inputs that are sometimes abruptly manipulated. Let's revisit each strategy with a focus on having a smooth, increasing plant input. Let's quickly review. Here's the input for each one. Revisiting the exponential 90% in 18 steps system, we'll now use an exponential ramp on the set point and see what happens. The plant input is now smooth. We now achieve 90% in 22 steps, which is not a bad trade-off to get a smooth plant input. Steps, 90%. We will use the exponential ramp set point system as a baseline, so let's adjust the remaining plots so that they achieve 90% in 22 steps. All the systems are now achieving 90% in 22 steps. Here are the results. Exponential, we're focusing on the input to the plant here. Linear with terminal value restrictions. Linear without terminal value restrictions. Smooth step and smoother step. Smoother step is slightly better than exponential ramp because every plant input is larger than the previous, all the way to the end of the ramp. Starting here, all the way to here, every value is greater than the previous value. Whereas the exponential had a larger first value, and the second value is essentially the same, but it's hard to beat the computational simplicity of the exponential set point ramp. Everything is a trade-off. Well, we had fun exploring set point slewing and the impact upon plant input and plant output. This concludes today's video. Thanks for watching.